Hi, Assalamualaikum to my beloved oral examiners. My name is NURSYAZA ATHIRA. As you can see, today I will be presenting to you my final year project. The title is Synthesis Chromium or Manganese Dope NCA Cathode Materials and their Structural and Morphological Studies. So there are 5 topics that I will discuss, which are Introduction, Literature Review, Methodology, Result and Discussion, and Conclusion and Recommendation. Problem statement. The increased use of petroleum products in our transportation networks has raised several worries about global warming in the Earth's outer atmosphere, necessitating the development of cleaner, carbon-free energy in the next decades. In the near and medium term, lithium-ion battery mostly uses cobalt as cathode. Cobalt is considered the largest material supply chain risk for electric vehicles. However, cobalt considered as the expensive element and toxic, so reduced cobalt content has economic, security, and social reasons. For example, cobalt is mined in Democratic Republic of the Congo, DRC, where children as young as 7 years old work in hazardous conditions, circumstances, and are subjected to extortion, intimidation, and assault. Significance of study. This research is being carried out to reduce amount of cobalt in NCA cathode. Cobalt causes many harms to human and environment. In this work, chromium and manganese was used as a dopant to stabilize the crystal structure of cathode materials after minimizing cobalt content. The objective of this study is to synthesize the chromium and manganese dope NCA cathode material using combustion method. Second, to study crystal structure of synthesized materials using X-ray diffraction. And third, to study the morphology and crystal dimension of synthesized cathode materials using field emission scanning electron microscope. Let's move to the chapter 2, literature review. First of all, as depicted in the slide, electrochemical storage devices are made of 4 basic components. 1. Negative anode electrode, 2. Positive cathode electrode, 3. Separator, and 4. Electrolyte. Next, cathode materials. Based on my research and what I had found, there are lithium nickel oxide, lithium manganese oxide, and lithium iron phosphate. For the modified cathode materials, there are lithium nickel manganese cobalt oxide and lithium nickel cobalt aluminum. There are 2 techniques to improve cathode materials, which are coating and doping. For surface coating is critical since it has been shown to improve cathode material performance by altering the surface chemistry or adding physical protection layers. Doping is a typical practice used to increase the material stability to modify the lattice constant or element valence. It typically entails introducing additional metal ions into the lattice. Let's go to synthesis method, shall we? So there are 3 methods that has been carried out by researchers nowadays in lithium-ion batteries. First of all, salt gel methods. The salt gel techniques is an efficient way to make high surface area materials. Second, combustion method. It may help tune electrode stoichiometry and morphology. It also increases electrolyte weighting and gives better ion kinetics. Lastly, cold precipitation method. This method is very simple to regulate and can give result in well crystallized powders. Now we have arrived at chapter 3, methodology. The starting materials, which are lithium nitrate, nickel nitrate hexahydrate, cobalt nitrate hexahydrate, aluminium nitrate nonahydrate, chromium nitrate nonahydrate, and manganese nitrate tetrahydrate. According to the picture, the starting materials that have been weighed according to molar ratio calculation was dissolved in deionized water at room temperature. Simultaneously, the citric acid also was dissolved in deionized water in a separate beaker. After that, both beakers holding the starting materials and the citric acid solution were mixed together and stirred for around 30 minutes. Following that, the solution was heated. The solution then was heated from 250 degrees Celsius until 400 degrees Celsius until it is burnt and the precursor was obtained. Chapter 4, Result and Discussion. We start with XRD. X-ray diffraction is used by researchers to characterize materials from a wide variety of environments. The lithium nickel cobalt oxide phases in ICDD database number 010871562 are used to compare the structural differences between each sample. The pristine NCA and doped NCA samples were successfully synthesized using the combustion method. As you can see the result, this data shows of RIR value and mean crystalline size of the materials calculated from Scherrer equation. It was found that the RIR value is lower than 1.2. This result shows that the cation mixing is high and make the performance of the electrochemical is poor. For field emission scanning electron microscopy, FESEM, used by the biologists, chemists, and physicists to view microscopic structures. Referring to this picture, it shows there is obvious difference in terms of particle size between the samples. All of them still in polyhedral shape. There are irregular particle size and uneven morphology for A, slightly agglomerate but not in regular shape in B, and C, the particle distribution are smooth. Last but not least, ETX, shortened for Energy Dispersive X-ray Spectrometry. It is used to validate sample purity and identify elements present in all synthesized samples. Also, referring to the data obtained, there are around 1% to 5% differences, either higher or lower than the actual percent atom present. The gap between the actual and theoretical percent is still considered to be an acceptable value, so these facts are still considered to be fairly good. Chapter 5, Conclusion and Recommendation. So, in conclusion, lithium nickel cobalt aluminum oxide NCA 1% chromium NCA 1% manganese NCA and 2% manganese NCA cathode materials were successfully synthesized using combustion method. The results of XRD and EDX analysis show that all materials were single-phase, pure materials. Based on the discussion above, all the synthesis samples have RIR values below 1.2, indicating a significant level of cation mixing inside the structure. There are 3 recommendations that I can simplify here. First, we need to conduct electrochemical performance for the synthesis cathode materials. Second, find other dopants that are more suitable to decrease the cation mixing. And lastly, we have to change the method used to synthesize the necessary cathode materials such as solvent method, cold precipitation method, and others.